Hi, I'm Stan Humphreys. My hobby is building and flying custom drones like this one in synchronized flight like this. Flying multiple drones in synchronized flight seems magical. The first time I saw a video of a drone light show, I assumed a master control station somewhere was controlling the drones remotely, or that they were somehow communicating between each other. Or maybe they were aware of each other using some kind of high-tech sensors or cameras. Well, robotics engineers doing research in a field called biological physics have used drones to simulate how real birds flock, and to do that, they used drones that did communicate between each other. But that's not how my synchronized flight works at all. In this video, I'll give you a bird's-eye overview of how my flights do work. Before the flight, I create a set of synchronized flight plans called trajectories using specialized 3D software. I think of this as designing the flight's choreography, as in dance choreography. I very carefully prepare these synchronized flight plans to prevent collisions between the drones and to respect their physical flight limitations, such as maximum horizontal and vertical flight speeds. Once that choreography is created, I create a master choreography file and take that file and copy it to my ground control station. Then, just before the flight, I upload these flight plans, a unique one for each drone, to the drone's autopilot. After a countdown, each drone takes off at precisely the same time. Then each drone's autopilot flies its unique flight plan completely automatically. So the drones aren't being controlled in real time via a radio link to the ground control station. And they're not communicating between each other. Each drone is flying autonomously, completely on its own. In fact, and I would never do this, after the flight begins, I could turn off all my ground radios and the flight would continue until the drones land, all completely automatically. Because each drone's autopilot is flying independently and automatically, there are no problems during the flight with radio interference from outside sources, or with data slowing down because of bandwidth saturation, or the drones can't fly out of range of a radio signal. There is none. For safety reasons, during my flights, I can immediately take control of any one individual drone or the whole fleet of drones. In fact, I have 3 independent command and control links to the fleet. As you watch the drones flying together, you may be asking, if those drones aren't communicating with a master control station, how can the timing be so accurate? Well, each drone, of course, carries a GPS receiver. The GPS receiver works by timing signals from the GNSS, the Global Navigation Satellite System, at nanosecond accuracy. So GPS receivers have clocks that are incredibly precise. Accurate timing is achieved by synchronizing the timeline of each drone's flight plan events, both their trajectories and their light effects, to the global GPS clock time. You might also be wondering, how can the drones fly so close together with such high position accuracy in 3D space? Well, my synchronized flights use a special GPS system called RTK GPS. RTK stands for Real-Time Kinematics. Here's how RTK works. Normal, non-RTK GPS systems are subject to errors when the signals from the satellites travel through the atmosphere, because the atmosphere is dancing around. Despite these errors, these days GPSs are accurate to about a meter, and that's amazing when you're navigating with your GPS during a hike or in your car. But for a fleet of synchronized drones, flying close together like that, 1 meter accuracy is not so great. That's why I use RTK. Here's how RTK works. My ground control station computer is connected to an RTK base station, which uses this large antenna. Before the flight, the base station surveys in to get very high 3D position accuracy. Now the drones are all connected to the base station using Wi-Fi. The ground control station uses Wi-Fi to transmit a stream of RTK GPS corrections to all the drones in the fleet. Each drone carries a special type of GPS receiver called an RTK rover, which receives the correction data stream. Then the rover uses the data correction stream to calculate in real time a very accurate position corrected for these atmospheric errors. So in this way, the RTK system increases each drone position accuracy from about a meter down to a few centimeters. It's very satisfying to see the drones land on their mats within a few centimeters of where they took off 10 minutes earlier. So that's a bird's eye overview of how my synchronized flight works. But how do I actually physically do it? Well, you guessed it. It's all about great software. And quite incredibly, it's all about free software. The software that powers my synchronized flights is from a young company based in Budapest, Hungary called SKYBRUSH. Incredibly, the engineers who created the SKYBRUSH suite of software tools decided to make an open source community version, which means the software I use to create and fly my synchronized flights is absolutely free. If you're not familiar with open source software, it's software that's released under a license in which users are granted the rights to use, study, change, distribute the software and its source code to anyone or for any purpose. And open source software is often developed in a collaborative public manner, meaning that if you're smart enough, you can contribute to its development. Now, SKYBRUSH software has been around for over 10 years. It's nice and mature. The engineers who created it use it themselves to design and fly their own drone light shows. SKYBRUSH is actively supported by the engineers who created it. They hang around in their forums and answer questions almost every day. New features are still being developed, tested, and added to the SKYBRUSH system. I'm a member of a large and growing community of SKYBRUSH users around the world. Earlier I mentioned that robotics engineers working in a field called biological physics use drones to simulate how real birds flock. Well, those very same smart engineers are the people who created SKYBRUSH. The SKYBRUSH system has several components. SKYBRUSH Studio for Blender is used to design the choreography. Blender itself is a very well-known 3D animation software package. It's also open source and free. SKYBRUSH Studio for Blender is a Blender add-on specifically for designing safe drone light shows. This is what my drone synchronized flight looks like when I designed it in Blender. Once the synchronized flight has been created, the drone choreography is saved to a compiled choreography file in the SKYBRUSH format. Then I use SKYBRUSH Viewer to visualize the flight and make certain it'll be safe to fly. For instance, this screen shows data about the minimum and maximum horizontal and vertical speeds of the drones, the minimum and maximum altitudes, and the minimum distance between the drones as the flight proceeds. Once the choreography is perfect, I can head to the airfield with my fleet of drones. The autopilot on each drone is called its flight controller. The flight controller runs firmware called ArduPilot. ArduPilot is open source, which again means it's free. ArduPilot is an autopilot system that supports many vehicle types: multicopters, traditional helicopters, fixed-wing aircraft, boats, submarines, and rovers. The engineers at SKYBRUSH have modified the multi-copter version of ArduPilot, which is called ArduCopter. The SKYBRUSH modifications to ArduCopter include the code necessary for the autopilot to accurately fly those trajectories and the light effects that we prepared using Blender Studio. At the field, SKYBRUSH Live is my ground control station. I use its smart checklists to prepare and configure my drones before the flight. Then I use it to start the flight and monitor the flight for maximum safety. So there you have it. That's the magic behind my synchronized flights. Thanks for watching.